So to verify the functor laws, we begin with the identity laws. The identity laws of fmap and of cmap can be verified simply by going through each case in the definition of fmap and see if applying them to the identity function instead of this function f, we get an identity function as a result. And this is fairly easy to verify. So for example, in this case, this is already identity function. In this case, f is identity, so the result is also identity. And here we have, by inductive assumption, fmap of g of f, fmap h of f are both already identity functions. So then we have a function that takes a pair GA-HA and returns again identity function of GA, identity function of HA, which is the same pair GA-HA. And so this is the identity function. Similarly here, we have, by inductive assumption, these are already identity functions, so we just have left of GA goes to left of GA, and so this is now for the function type. We have this definition. Now, if this is already identity function, and if this is already an identity function by inductive assumption, then we just have a function that takes p and returns p. That's the identity function. Here, by inductive assumption, this is an identity function, and this is an identity function. So this is just fmap g1 of f, but that's also an identity function because f is identity. And so by inductive assumptions, both fmap of f, which is the recursive function we're defining here, and fmap g, they're both satisfying the identity law. So when you apply them to an identity function f, you get again an identity function. So here I just wanted to note this definition is recursive because we're using fmap f in the body of its own definition. And so when we prove a property of fmap f, the inductive assumptions include an assumption that the law we are proving already holds for recursive calls of this function. So that is a standard way of proving properties of recursive functions. And finally, for the universal quantified type, by inductive assumption, this is the identity function. So then we have p going to x going to p of x, which is just p. So that's the identity function for p. And similarly, we go through all the inductive cases for contravariant functors, and we get again that it's in every case cmap g of an identity function gives again an identity function. The composition law takes a bit more work to verify, but we do exactly the same thing. We go through each case, and then we have to write a little more derivation. So I will show just a few cases. For example, case 3 for fmap, which is a tuple, which is defined like this. Now, the composition law says that for any function f and g, for any function g, and for any values of these types, we can apply the left-hand side of the law, which is this one, or we can apply the right-hand side of the law to this pair, to the tuple, and we should get the same results. We should get the same values. So let's verify that this is the case, assuming that this already holds for fmap g and fmap h. So then, so we take the definition, which is this, and we write it out. So fmap f of the pair is a pair of these two. Then we apply fmap f of g to this pair, applying that to this pair gives us a pair fmap g of g, fmap g of f of ga, fmap h of g, fmap h of f of ha. Now, by inductive assumption, this already satisfies the composition law. So this composition is equal to fmap g of f and then g. And similarly, this composition is equal to fmap h of f and then g. And so this is then exactly the same as when you apply fmap f of f and then g to the pair GAHA. So we get the same result as this, assuming that the law already holds for fmap g and fmap h. So that is the inductive assumption. And the next case, we will prove the composition law for cmap in case 5. Now, case 5 is a function type. So this is a little more involved. The definition is like this. And we apply both sides of the law to arbitrary value kc, which is of this type. So because this is a contramap, we contramap with AB and with BC, and the result will be that we map backwards C to B and then B to A. So the result will be a function of type G of A to H of A. So let's write it down. We apply this to KC, we get this. Now, fmap G of G, and then KC, and then cmap H of G. So we now have to apply cmap F of F to this. So let's write what that is. Cmap F of F of this is writing it out. So it's just a lot of function compositions. And the function compositions are associative. So we can just say this, compute this first. And by inductive assumption, it is fmap G of F and then G. And so this remained as it is. And then we have this composition, which again gives us, by inductive assumption, cmap H of F and then G. Now this, in my notation, I'm using cmap underscore H here, so let me correct that. So in this way, we show that the law holds also for cmap F, if it already holds for cmap G and cmap H. And the last case I'm going to show is that we want to prove the composition law in the recursive case 6. So case 6 of fmap, it is, it is this case. Oops, no. It is this case. So let me just make a little different. Yeah. So it is this case. The case 6 for recursive types. So then, in order to verify that, we need to write down the definition of fmap F. I'm just copying from case 6. This is a recursive definition. Now we apply both sides of the law, the left-hand side and the right-hand side, to some values. Actually, yeah, this is not necessary. I have simplified the proof. since then, so we don't need these values. We just need two functions f and g, and because the law is written without writing out the arguments of functions, so it's like a function and then another function, so it's a what is called a point-free style of writing functions, where we don't write the last arguments or some of the curried arguments. And that makes the proofs shorter. So the left-hand side of the law we can write like this. It's fmap of g1, and then there is this, and then all these other fmaps. And the right-hand side of the law is written in this way. So we can expand fmap f of f and then g by composition law, because this is a recursive call of the function fmap f. So we can expand it like this. This is an inductive assumption. Then we expand this as well by inductive assumption. And then we have fmap g of a composition, which we again expand by inductive assumption. So then we have a composition similar to this one, except that the order of some functions is not the same. So the first is the same, and then the second one is not this. The second one is here. So what we need to do is we need to put this one to the right of this one. Well, we cannot just put it there, right? We derived that the functions are like this. So the difference between the left-hand side and the right-hand side is now only in the order of composition between these two functions. So this and this. If we change the order of composition, somehow, if we prove that we are allowed to change the order of composition without changing the value, then we will have proved that the left-hand side equals the right-hand side. So this is a commutativity law of this bifunctor G. The commutativity law says that you can lift with fmap with respect to one type parameter, which is what I write here as g1, and we can lift with respect to this second type parameter of g. G has two type parameters, and we can lift this in any order. So it's similar to the composition, to the commutativity law that I showed you here for the profunctor, where you can lift in any order. You can first lift in the first type parameter, or you can first lift in the second type parameter, and then in the first. The result is the same. So now we show that the commutativity law is necessary for the functor law to hold. It's actually necessary to assume the commutativity law. So we will show that commutativity laws hold later. Right now, we'll just assume as a requirement that the commutativity law holds. But what we will prove later is that any fully parametric type constructor with two type parameters always satisfy the commutativity law. And the reason is that commutativity law is just a naturality law. And you see, it's naturality law is the law that says that your function can commute with an fmap. So if you apply fmap after the function or before the function, it's with suitable changes in type parameters, the result is going to be the same. Now, this is exactly the same law where you apply fmap either before or after applying the cmap. So this, you can see, this is a naturality law of this function, cmap. And if this function is fully parametric, the naturality law holds for it due to the parametricity theorem, which we will prove. So right now we have not proved it, so we need that as an assumption. But essentially, the functor laws hold as long as everything is fully parametric. And right now, what we have seen in the definitions of sorry, not the right slide. In the definitions of fmap and cmap, what we have seen is that all the code that is generated for fmap and cmap is always fully parametric. So we can actually generate this code mechanically by looking at the type of the type constructor. We can generate mechanically this structural induction. We can go through the cases and then recursively through all the other cases as necessary until we get to the base cases of the induction where we just write code directly. And we can mechanically generate the fmap and cmap code that is going to be automatically fully parametric, because as you can see here, all this code is always fully parametric. So all this, it's always fully parametric. And then we will prove later then that fully parametric code always satisfies naturality laws. So that means we are going to have those assumptions always satisfied. So the assumption that that we need a commutativity law is always going to be satisfied. So let me summarize the first part of the derivation. We have shown that we can derive fully parametric code of these functions from the type expression. So this is the standard code for fmap, cmap, and xmap that is going to be used by all naturality laws. Also, we found that the consistency of the definition of xmap and the functor laws for recursive type, also for the universally quantified type, I believe, but actually, they require a commutativity law. So these commutativity laws will follow later from the fact that this code is fully parametric. So we are trying to avoid too much derivation. So we first just show that this code is fully parametric, which is clear just by looking at this code. And then we will prove later that all fully parametric code satisfies the naturality laws. And the naturality laws use this code. So this is what we do when we write a naturality law. We write specifically this automatically generated code of fmap, cmap, and xmap.